Suppose you built yourself a walking robot. It consists of 2 legs and a torso. You want to make it as energy efficient as possible, as it has to carry its own battery pack. So you decided to only use a single motor which is attached between each of the legs in order to make it walk. But you have to keep the torso upright while walking, so you have decided to put a pair of linear springs between each leg and this torso. These springs are such that you may tune the spring stiffness if you so desire in advance. Now what remains is for this robot to walk. So you need to find some sort of walking gait, and you have to build some sort of feedback controller in order to make sure that it can handle some uncertainties and disturbances. For instance, if you have some headwind while walking and so forth. So in this video, I'll hopefully help you answer or give you some way of solving these 2 issues. So in order to help you solve these 2 tasks, that is planning a walking gait and to make a feedback controller, we will utilize the approach which was suggested in our paper as seen here, which was presented at the European Control Conference in Naples in 2019. So we will consider in this video the simplest type of walking gait, which is called a so-called symmetric gait. And we'll consider it as the search for a so-called hybrid periodic solution. So what does that mean? So let X denote the states of the system. So it consists of the joint variables which describe the pose of the robot at any given time, so where the legs and torso are, together with their velocities or the joint velocities. So if we start with a given state, so at this given pose and with some joint velocities, then we will look to try to find some sort of control input such that the states evolve. So that is the back leg detaches from the ground, swings forward, so it's called the swing leg, and the leg which is in contact with the ground is called the stance leg, such that this swing leg swings forward and then it touches the ground at an end pose, which is identical to our initial pose, only that the legs have swapped roles. So the stance leg will be the next swing leg and vice versa. Now when it hits the ground, an impact occurs, which we model as an instantaneous mapping, F, which takes us from our current states back into our initial states and so forth. It repeats. So what we're looking for is starting from some pose or initial state, find a continuous control, which then brings us onto another surface, which is such that this impact mapping takes us back where we started. Now the next task then, if we can find such a periodic hybrid periodic solution, then we want to design a feedback controller for it, meaning that if we, for instance, start with our states up here somewhere, then we want to use this feedback controller to bring the states over time back into this periodic orbit, which is formed by the solution. Now, neither of these tasks are very easy, both the trying to find the solution, or a trajectory as it's called, or to trying to design a feedback for it. So the first thing, any such trajectory have to comply with the dynamics of the system, especially the dynamics which arises due to the underactuation of the system. So what is underactuation? Or very simply, we have 3 degrees of freedom or joint variables describing the pose or configuration of the system. But we have only 1, or for that matter, 2 actuators which we can use to influence the system. Now, this means that what we can make the system do, the motions, is limited by this underactuation. For example, if you're out for a walk, try stopping in the middle of a step. It's more or less impossible. And this is why when you have a walking robot with underactuation, it's what's called dynamic walking, or basically controlled falling. So the robot keeps falling forward, but we use our controllers or our motors to compensate for it and then to make this controlled falling into a walking gait. In addition to these dynamics arising due to the underactuation, we also have to satisfy path constraints which are imposed on the system. So this might be bounds on the states, so we can't have infinite leg velocities, and on the actuators or the motors, so we can't have infinite torques of our motors as well. Of course, we also, if we find such a gait, we have to make sure that actually when the swing leg moves forward, the stance leg should not detach from the ground before we have actually ended the step. Otherwise, we would start running rather than walking. And that we want to make sure also that we are not so aggressive that the stance leg slips and so forth. So there are many things that has to be checked during this step, during a walking gait as well. Lastly, we also want such a gait to be reasonable by some sense. So if we have this battery pack attached to it, we want to, for instance, use the least possible amount of energy such that we can walk for as long as possible. Perhaps there's limitations on the torques of the motor, so we want to keep the maximum torque as low as possible during the walk. Or we perhaps want it to be the fastest possible walking gait within the dynamics and bounds, so it's called minimum time type of walk. So there are several things which have to be satisfied for every such walking gait. If we find such a gait, then we have to stabilize it, because most often, almost all these types of walking gaits will be so-called open loop unstable, meaning that without any feedback, just the tiniest of perturbation will eventually lead to instability, making the system fall over or not being able to keep the walking gaits for very long times. Also, even if you find a controller, it will most often have a very small region of attraction, and it will be very difficult to find. So you have to find some sort of controller which you actually can find, which handles both the continuous phase and the impacts which occurs, and which also has the largest possible region of attraction. Now, the approaches I will present in this video are based on the following idea, namely that for one, we assume that if we can find a solution such as a walking gait described by some evolution of the states, then this can be described as the synchronization of the states through a so-called motion generator. So what does that mean? Well, basically, if we can find some sort of solution denoted by the asterisk subscript, then this might be parameterized by some sort of scalar variable s. So you can think of it sort of like a reparameterization of time along the trajectory. It differs from time in the sense that it can be recovered from the states of the system, meaning that if you know the state, so the pose and velocities or configuration velocities of the system, then you can find S through a so-called projection operator. Now this means that you then can find, for the given state, what should the corresponding joint variables be and their velocities and so forth at any given time. Now this synchronization has also a value in terms of trying to design feedback. As, for instance, if the states are up here, then we can recover the corresponding S, which would be the point here along this normal solution, and then we can measure the distance from the normal solution back up to the current states. And then if we can design a controller which for any such perturbed states can enforce contraction, so such that if we start here, then we will move towards the normal trajectory as S moves in time. Then we can also design controllers using these types of schemes. So it's useful both in terms of the planning and in terms of control design. So more specifically, by assuming this synchronization of the states using this motion generator, we can for one reduce the dynamical constraints which arises due to the underactuation down to a series of ordinary differential equations which are integrable, the number of which are equal to the degree of underactuation. Now these we can then again use to state a quite efficient to solve trajectory optimization problem. So we can state it as an optimization problem, which we then can solve numerically in order to find solutions. Then if we're given a solution, then we get a straightforward choice of so-called transverse coordinates. So these are sort of like the distance or this distance from the normal orbit and the given state as shown on the previous slide. And these coordinates, if we can then stabilize their origin, which is basically which corresponds to the desired solution, then we stabilize the corresponding walking gait or periodic solution in what's called the orbital sets. More on that later. And this then allows to design so-called orbitally stabilizing time invariant feedback in the sense that it only depends on the states in order to stabilize it. Now, these ideas are not necessarily new by any means, so there are many papers on these types of ideas, but we have our own twist, and we also provide a numerical framework to solve these types of problems in both the paper and in this talk. So as we saw, the idea is to introduce so-called set or synchronize the states through a so-called motion generator. And for this, we'll introduce a so-called set of synchronization functions. Let us first introduce the dynamics of these types of systems. That is, we may describe the dynamics or the equations of motion of this system as underactuated Lagrange as an underactuated Lagrange system with an impact described by some sort of instantaneous or discrete jump. So I won't go too much into detail on this system, but basically the dynamics may be written in this form. Here Q are the generalized coordinates. Q dot are the derivatives or the generalized velocities. Q double dot their accelerations. We denote by X the states, which are just the configuration, generalized coordinates and their velocities. And U are the control inputs, of which there are M, which are less than degrees of freedom, since we assume the system to be underactuated. Now, if the states enter into some sort of switching surface, denoted by gamma minus, then we assume that they will be mapped to some other surface, gamma plus, through the mapping F. So basically, if they enter into this surface, then they will be mapped back, and then the continuous phase are then described by the Lagrange equations. So with this in mind, suppose that we have found such a solution of this system, denoted by the asterisk subscript, and together with the corresponding nominal control input. This solution is described by now a hybrid periodic orbit, which is then just a set of all the states along this solution over the given time interval. Now let us assume that we know a reparameterization of this solution. That is, we know some sort of function phi consisting of a set of basis functions, so polynomials and so forth, parameterized by S, where S is a motion generator. So basically, it is strictly monotonically increasing in time, meaning that its nominal velocity is strictly positive over a given domain, which may then be used to describe this motion using these basis functions with a set of parameters P, which might be, for instance, polynomial coefficients and so forth. Likewise, its velocity nominal velocity may be described as follows, with the prime corresponding to the derivative of phi with respect to S, and the nominal control and the nominal acceleration as well may be described using S and its velocities. So the function phi is what we call so-called synchronization functions. So it consists of these scalar functions for each generalized coordinates parameterized by S, given a set of parameters P, so polynomial coefficients and so forth. So why do we consider such parameterizations? So let's just assume that we have found such a parameterization such that the nominal motion might be described in terms of S. So if we insert these synchronization functions and their derivatives, as well as the nominal feedback in terms of S, back into the continuous time dynamics, then the following must be satisfied. So the dynamics have to be satisfied given a solution. Now notice here that it's only described in terms of S, its velocity and acceleration, as well as these synchronization functions. Now we might rewrite these dynamics if we have assumed the invariance of these relations as a series of first-order differential equations in terms of S, its velocity, and its acceleration. Now if we have M actuators, so M motors, then M of these equations have a right-hand side, which corresponds just to one of the control inputs, whereas the remaining N minus M equations, their right-hand side is 0. So basically, for M of these, we can have any evolution of S as we want within the bounds on the actuators, of course, but still we can just choose U in order to get the desired behavior as we want, more or less. But we will, if we have underactuation, have N minus M equations whose right-hand side is 0, and which then determines all the possible evolutions of this motion generator S, meaning that its time evolution cannot be any. So if we take a specific choice of these motion generators, then all the solutions or trajectories then formed by this choice of synchronization functions are described by the corresponding evolutions of S, which satisfies these sets of equations, which are sometimes called the reduced dynamics or the alpha, beta, gamma equations due to the functions which arise here. So these reduced dynamics, this alpha, beta, gamma equation is therefore very important in terms of then planning motions for a system. That is, any feasible trajectory of such a system must comply under a choice of synchronization functions with these equations. So when we want to plan a motion, an obvious way is then to try to pick a synchronization function and see what types of motions are possible given how they satisfy these reduced dynamics. It turns out that these equations have actually several nice properties. For instance, they are integral in the sense that first, if we use the relation between the double derivative of S, which may be rewritten as 1/2 the derivative of s dot squared with respect to S, it's a well-known relation. You can try to find it yourself if you're not familiar with it. Then it's quite easy to see that this equation here has an integrating factor given as follows, with delta defined as here, given as beta minus the derivative of alpha with respect to S. Now, since it's an integrating factor, we can therefore integrate, and we may therefore define a function I, which takes in the initial point of S, its initial velocity, and S and S dot, defined as follows. And then for any S and S dot which satisfies or makes this function I vanish, corresponds to a solution of this reduced dynamics or this alpha, beta, gamma equation. So it looks a bit hairy, I know, but it isn't too bad. And what its use is basically then, if you pick a set of synchronization functions, which will then determine what the functions alpha, beta, and gamma, and for that matter, delta is, then by evaluating this function here, so if you can check all the values of S and S dot, which makes it go to 0, given an initial set of values, if it's 0, then you know that this actually corresponds to a true evolution of this motion generator, and you may therefore use it to plan trajectories or to check that the dynamics of the system are validated along a feasible trajectory. But again, it's quite hairy. We have these exponentials and so forth, with delta in the numerator and stuff like that. Luckily, for some types of systems, especially those in which, if you have an underactuated system, in which the first generalized coordinate in a kinematic chain is passive, so unactuated, then it goes to 0. And this will, for instance, be the case for the joint describing the ankle of a biped walking robot, meaning that for this, we might simplify, we might set delta equal to 0, and we have this quite a lot simpler expression. This might also make it more intuitive in the sense what this function I is. In a sense, it's like the level sets, energy level sets of these equations. So we might in a sense just consider it as that we want to keep an energy level set during a solution. So this brings us to stating our motion planning scheme. So how we can actually try to find such solutions corresponding to walking gaits for this system. So when you have such a problem in which you want to try to find some sort of trajectory of a dynamical system, it's common to state it as a trajectory optimization problem. So we've tried to find a solution which describes a trajectory of a dynamic system, satisfying properties as you want, and often to minimize some sort of cost function. That is, we have some sort of cost function, L, which is described in terms of the states and the control inputs. And it's defined over some sort of desired period. So it should end after capital T time has gone. This has to be any such trajectory has to satisfy the dynamics of the system, written here on regular state space form. It has to satisfy some sort of initial pose and some final pose. And together it has to satisfy such that the initial states just corresponds to the final states mapped through this impact mapping F. Now, what we suggest is to restating such a trajectory optimization problem using the synchronization functions and using this integral of the reduced dynamics as we saw on 2 slides back. That is, if we represent the states x in terms of the synchronization functions, parameterized in terms of s, and likewise we can do the same for the control inputs, then the objective might be written here as the integral from the starting value of the variable s to its final over the corresponding objective function described now in terms of s, its derivative, as well as these parameters of the synchronization functions. If we divide by its velocity, then we might consider it this integral over the period of s. And recall here that s dot is assumed to be strictly positive over trajectory, so there's no problem in the dividing here by s dot. So the integral, the dynamic constraint may now be written in terms of these integrals of the reduced dynamics. So in a sense, if you have 5 degrees underactuation, you should not do this, because then you should have a series of discrete sampling points along it, as even though 2 integrals for different reduced dynamics might both go to 0, it's no guarantee that they will correspond to the same solution. But if you have, say, 1 degree of underactuation, then you will have 1 integral, and then it's enough to just check this integral over the given period. Likewise, you want your synchronization function to correspond to the desired initial and final pose, given the initial and final value of your motion generator. And likewise, you want your states parameterized in terms of the motion generator to satisfy this impact relation. So basically, I've rewritten all this problem in terms of the synchronization functions. And our variables now is the parameters of the synchronization function. S, we can choose its domain, so it's not the optimization variable, but the velocity of S is still a variable on a search, actually infinite dimensional, as we have to have it at all points along this solution. So we have some infinite dimensional optimization problem we're trying to solve. Then we have to try to find some way of discretizing this problem in order to be able to solve it numerically. Now, in this regard, in order to discretize this optimization problem, we suggest using Gauss-Legendre quadratures, although any other type of numerical quadrature can be used instead, just to approximate this integral or this objective. That is, we pick a series of node points, Si, and corresponding weights, Wi, corresponding to the Gauss-Legendre quadratures, and evaluate this objective function at these points. But we need to know the velocity of the motion generator, so s dot. So in order to do this, we introduce a new set of decision variables, capital Si, which are then defined as the velocities of the motion generator, its square, evaluated at these node points, as well as the initial point and the final point, so with subscript 0 and m+1. The dynamics may now be checked in terms of these integral functions. That is, we may then evaluate it over each of these intervals of the domain of the motion generator, meaning that we just have to check it for each j going from 0, 1 up to n as follows. And then if these evaluate to 0, then we know that the dynamics are satisfied over this given this trajectory. So let's actually show that it works in an example by actually trying to find walking gates, symmetric walking gates for this 3-link biped robot. That is, we want to find a symmetric gate of this biped robot in which the synchronization functions, which are parameterized in terms of S, are described as Bézier polynomials. So enforcing this results in 3 first-order differential equations in terms of S and its velocities, in which the last one corresponds to the right-hand side to the motor torque, which is attached between each of the legs. The second one we have denoted by U1, whereas the first one is passive. Now U1 we want also to just try to find to just use the one motor, the one between the legs, in order to make the robot walk. So while we might evaluate the integral, this will result in an integral in which this delta on the previous slide, if you recall, will not be zero. So it's a bit nasty to evaluate, fully possible, but making the optimization problem, gradients and so forth is somewhat not the most fun thing. So instead, we assume this the absolute value of this control input, that is, we just take the absolute value of the left-hand side, should be less than some epsilon, which should be very small. So which will merely correspond that if this epsilon is taken small enough, then basically this corresponds to a gait which needs one actuator in order to walk, and then we design a feedback to compensate for it. So the length of a step is shown here. So basically we have a symmetric gait, and then we might find the step length. Choosing the step length, we might find the initial position of the first generalized coordinates. And likewise, we wanted to satisfy the following relabeling at the step and the following impact map, in which this impact map PQ dot is found using standard methods, which you can find in the references given in the paper. So by solving this trajectory optimization problem using MATLAB, you can see how this is done in the paper. This is a gait, one of the gaits found. So basically, you can see here the velocity of the motion generator over its period. So it's not constant. This is so if it corresponded to time, for instance, it will just be equal to 1. But we see that it changes during. So we have this extra layer of flexibility instead of then enforcing that S should be equal to time. We see that the motor between the legs goes well within plus minus 50 Newton meters, whereas this second motor is well being in between 10 to the minus fifth, so basically close to 0, and our feedback should be able to handle this as a very weak disturbance into the system. And here we have the phase portrait of each of them and so forth. So before we move on to designing a controller for stabilizing this found periodic solution, I want to briefly mention that we can use, or at least quite easily modify, this trajectory optimization problem to plan trajectories for other types of systems as well. So in order to demonstrate it, let's look at the following. So here we have used it to plan a so-called swing-up motion for the well-known cart pendulum system. So we start the system from the bottom bottom position. It is a cart. It has some acceleration, so you can move from left and right, but attached to it is an unactuated pendulum. So we have 1 degree of actuation, and the task is then to swing it up. And as this video here shows, this is a planned trajectory using this approach. And so we can use it to plan trajectories for other types of systems as well. So that brings us onto the second part of this talk, which is how to design a controller for this problem. So as is common, we divide this controller into 2 parts. So the first is just some part which recovers the nominal velocity when on the nominal orbit. So there are many examples of this part. For instance, one example is shown here, in which the function zeta recovers the nominal velocity of the motion generator and is a function of the motion generator itself. But the only requirement upon U asterisk is that it recovers or is equal to the nominal velocity when the system has converged to the nominal orbit. And then secondly, we have this feedback part V, which we'll use to design some orbitally stabilizing controller. So this brings us back to this figure, which we saw earlier in the talk. So we assume now that we have already found some sort of nominal trajectory parameterized in terms of S. So we have solved this trajectory optimization problem, and it has given us some desired trajectory which we are satisfied with. So now we want to use this to design an orbitally stabilizing feedback controller. So again, the plan is, if given some state, we can recover the corresponding value of S. That is, we can project down upon the nominal orbit, then we can get some measure of distance to it. Now this lets us introduce what's called a set of transverse coordinates, whose origin corresponds to the nominal solution. And so if we can stabilize the origin of these so-called transverse coordinates at all points along this hybrid periodic orbit, then we simultaneously stabilize this orbit as well. So this is what's called so-called orbital stabilization, in the sense that we consider stabilizing the periodic orbit, the set of all the states along the solution, and not some particular solution time leaf which moves along, so not regular reference tracking control. And this has several benefits for these types of problems. But in order to utilize such a scheme, we need some way of recovering this motion generator. That is, we have to find some so-called projection operator in order to recover it. So one way of finding it is through the following. So assume that there exists some scalar function h, which vanishes on the nominal orbit. So if the state's given on the nominal solution, and its derivative with respect to s is not equal to 0. Then one can take or find s through some mapping p, a so-called projection operator, which is such that for all x close to this nominal orbit, we can take h as such and it will vanish. And then by the implicit function theorem, we can then find the corresponding gradient of p as using the following formula. So this means that we can recover, if we know such a function h, then we can find this s through this projection operator p. And just to mention that, such a function can always be found for these types of trajectories. So suppose now that we have found a nominal solution, a projection operator. This then brings us to choosing a so-called set of transverse coordinates, as I mentioned earlier. These are a set of 2n minus 1, so we have 2n states of the system. So there are 2n minus 1 independent such coordinates, which we denote by xperp, and which then naturally have their origin on this nominal solution, so they vanish. The reason there are 2n minus 1 is like the same as we saw on this figure 2 slides ago, that they have to be defined transverse to the flow of the orbit. And hence we are only concerned with stabilizing the transverse direction in order to ensure contraction to the orbit. So we do not have to consider the direction which is aligned with the flow of the normal trajectory. So we have, with knowing this parameterization of the orbit, so knowing this phi and the nominal velocity of the motion generator, we have a series of coordinates or candidates to choose as transverse coordinates. So the simplest one is just y, which is just a given configuration minus what it should be given the synchronization functions. Its derivative. We may also define, so if we swap out the velocity s dot with the function theta, which recovers this nominal velocity given a value of s, then we can define c as follows. Or we can define the scalar rho, which is just the difference from the actual velocity of s and what it should be given its corresponding value. This, in a sense, is more or less identical in some sense to the function I, which we use to plan, which then gives these energy level sets which we want to keep to 0. So we have several of these candidates. What you have to do is just to try to find 2n minus 1 of these, which are independent at all times. Although it's also necessary to just pick 2n of them, which are then an excessive set, and use these as well. For simplicity, we will have, however, assumed that we have picked or found 2n minus 1 independent such coordinates. What we want to do then is to stabilize their dynamics. So the dynamics of these coordinates can be written on this form shown here, just using the Jacobian of these coordinates and using the regular equations of motion, so the Euler-Lagrange equations. And this results in the following system if we have chosen a feedback, as we saw earlier. Now, in order to design a stabilizing controller for this system, we want to linearize these dynamics. That is, we derive the so-called linearized transverse dynamics, which is such a system, a hybrid periodic linear system, in which at a given endpoint of this motion generator goes through a map, which is defined here as like a sort of a differential of the mapping f in the transverse direction. So more on this in the paper, but what we do is then we want to design a controller V which stabilizes this linear system, which varies with S, and which is subject to this map at the end of the orbit. And then we can use well-known controlled strategies in order to solve this problem. So for those interested in seeing how one can actually solve and design a feedback using this linearized transverse dynamics, you can look at the paper, which is down in the comments. So here is an example of how a controller is designed. So this is a controller. We have designed a controller and then implemented it on the system in MATLAB. Just let us see that it actually works. So here it is. It has just a single actuator between the legs and the hip, but we had this, if you remember when we planned the trajectory, we had this, we assumed that we had this artificial actuator, which we wanted to make very small, so its absolute values would be on some epsilon, which then is just some basically like a weak disturbance into our system. So let's demonstrate that it works. So we started with some perturbed initial conditions, and few steps later it converges, and we see that here you see the transverse coordinates y goes to 0. Likewise, the transverse coordinates zi, these are defined in the paper, you can have a look at them there. They go to 0 as well after about 3 seconds. And we see then that the robot walks smooth and well. You can see at the beginning that you have this sort of wobble, so we have some saturation and stuff like that here, and some straight leg movements. But this, again, remember, it has a single actuator together with some linear springs, which we have also searched for the spring coefficients. Again, look at the paper. And still it's able then to recover from this these perturbations and walk stably afterwards. Okay, that brings us to the end of this video in which I presented our paper. So we have gone through quite a lot of material in what's a relative short amount of time. So it becomes very superficial, and I just go very fast through each of the steps. So if you're interested in learning these types of approaches further, please feel free to look in the paper, which I've given down in the information of the video. And to the references there, and also to the other conference presentations and videos I have put out on my channel. If you are also interested, feel free to contact me and I'll be happily describe in more detail, or if there should be demand, I'll also happily try to perhaps make videos in which I go into each step in more detail, so a bit more tutorials in a sense. So just let me just end with a brief summary of this approach and how this both the planning and control ties nicely together with this approach. So we have assumed, or we have been looking for a first step to find some trajectories, or starting with initial state, find some evolution of the state using the control input, which are consistent with the dynamics and path constraints and so forth, especially the dynamic constraint due to the underactuation, such that we evolve to some final desired pose, and then the impact mapping takes us back to where we started. Now we solved it by looking for a set of synchronization functions, which were described in terms of this variable motion generator S, which was sort of a reparameterization of time along the trajectory. Now this motion generator gives us an extra layer of flexibility when trying to plan this problem, as in a sense we may let time vary along the normal trajectory. Now this means that we can represent such a normal solution with, for instance, polynomials of quite low order compared to if we say try to do the same with time, as we let the parameterizing variable s vary, its velocity vary along the normal trajectory, giving us this extra layer of flexibility. Now we showed that this could reduce the dynamic constraints of the system down to only a few first order differential equations, the number of which equal the degree of underactuation, and which then let us state a quite efficient to solve the trajectory optimization problem, which then could give us a trajectory as desired, and which then could be used to find a walking gait for a robot with 3 degrees of freedom, but only a single actuator. Now, when we found such a trajectory, this approach also showed that we could then easily define a natural set of so-called transverse coordinates if we could find a projection operator to recover the variable s. That is, these transverse coordinates, they have their origin on the nominal trajectory, but are non-zero away from it, such that if we stabilize their origin at all points along the trajectory, then we naturally also stabilize the periodic solution in the so-called orbital sense as well. So we have this nice combination of an approach which both let us plan a trajectory and then in a sense also gives us a way to design a controller as well.